Hey gang, Math 1500. The title of this video is probably uh, best. I can't I cannot speak and write. It's crazy. Approximating a binomial distribution with using a normal distribution. Sounds glorious, right? All right. So, guys, what essentially I want you to start thinking about here is kind of a switch to categorical variables. But the categorical variable that we're looking at here is dichotomous. And dichotomous just means we have one of two outcomes, hence binomial. Now, but in kind of in the broader study of statistics, what we just did is we looked at normal distributions, and we looked at normal distributions of quantitative variables. For example, IQs, numbers, ACTs, numbers, SATs, numbers. A gestation period would be in days, so therefore numbers. But we're working into something now which is going to be a categorical variable. Hence, it's like a yes or a no, or a true or a false. Again, because we're looking at binomial, where we have one of two outcomes. For example, we'll look at a problem here in a minute. Calculate a probability that a kid is either on drugs or they aren't, a middle school kid. You're either a Kentucky fan or you're not. You're a Ohio State fan or you're not. You're a Republican. Just all sorts of things that we run into in statistics deals with one of two outcomes. Now, a couple of things I want you to think about. First of all, some properties of the binomial distribution. And these are just, let's just call this properties. And just to kind of get you kind of, thinking in terms of binomial responses compared to a quantitative that we've been dealing with here for about the last 3 weeks. First of all, we have what I would call n identical trials. So we have an experiment, if you will, that consists of a fixed number of n trials. Second thing that's important, each trial is independent. So another thing I want you to think about for independence is just that the trials are not related. In other words, picking the second trial has no impact on the third trial. I tell you what you get into a lot if you ever go to Las Vegas or any of the casinos around here. Even if you play roulette, you see people that will sit there and they'll watch the colors and they'll say, well, there's been like 7 black in a row. It's time for a red to hit, right? Now, what actually probabilistically, what's happened previously, if that spin is truly independent, which we assume it is, or at least they assume it is in gambling, then what happens on that next event is completely independent of where that ball landed on the previous roll. Let's see what else. Okay, each trial has 2 outcomes. We talked about that already. If we were talking about a blackjack, you either got blackjack or you don't. Sounds like I missed Belterra, doesn't it? Haven't been in about 3 weeks, so maybe. Anyway, it could be the ball lands on red or it doesn't. What else do we have? The probability of I don't know how I want it. Let's just call it the probability of a success. That's be a good way to put this. is called P, and the probability of getting a failure is called 1 minus P. Now, success and failure I put in quotations because, you may be interested in the probability that the next child born at a particular hospital is female. So that would be a success and a male would be a failure. Well, you don't mean that a male's a failure. It's just the success is what you are measuring the probability of. For example, what's the probability that the next ball on a roulette wheel lands on red? Well, success is landing on red, failure is not landing on red. Well, not landing on red is not a failure to the person who bet on black. So this whole success failure thing is kind of in the context of the problem. The random variable, I guess. I tell you what, let's go on and get into the parameters here, and I'll do that on the next page. Okay, apparently. All right. On the next page, if the conditions now. If our conditions are met, and guys, our conditions are very simple in these types of problems. All we need is n times p to be greater than or equal to 5, and n times 1 minus p also to be greater than or equal to 5. So if these things are met, then a normal distribution can be used to approximate the binomial distribution. And what we see here, and guys, again, remember, a normal distribution is defined by its center and its spread. Just to, again, to give you an indication, if we've got an axis here, and I'll do something just really quickly, and we say we've got a normal distribution that we want to draw on this thing. Well, if we know the mean, we know that that distribution is centered right there. Well, that's actually, I can't even read my own writing, so let's say 20. And we also need to know the standard deviation to know an indication of spread. So when I know the mean and I know the standard deviation, then I define my normal distribution. So to approximate this binomial distribution by a normal distribution, we have to know what the center and spread are. Well, it turns out the center for this type of distribution is the mean mu, which can be found by taking n times p. The spread of this normal distribution can be described with the standard deviation, and this is given as n times p times 1 minus p. Now, some notation that you see, and I see this in a lot of other textbooks, we can just say that mu is equal to p and sigma is equal to the square root of p times 1 minus p over n. So I will illustrate that to you in a couple of problems, okay? Now, I know right now this stuff seems a little weird when you first start looking at it, but just hang with me, and we'll look at some examples here in just a second, which I think will clear up some of the kind of the vagueness. Now, first thing we run into is when we take a categorical response. And here we're looking at a binomial response. So it's one of two things: true or false, success, failure, this or that. And we try to model this with a normal distribution. Pretend that's an n, which is quantitative. Well, we've got some issues. And the issues are we have to come in and implement what's called a continuity correction. Now, a continuity correction, all this thing does is it takes a discrete value. And guys, what's meant by discrete? Countable. I can't count your IQ. I can measure it. I can't count your weight. I can measure your weight. I can't count your ACT. I can measure your ACT. But I can count the number of TVs you have. I can count the number of horses that you've ridden in your life. I can count the number of calculators that you have. So when something is countable, we have something that's called a discrete random variable. Well, what we have to do, when we have a discrete distribution like this, we have to implement what's called a continuous, we have to implement what's called a continuity correction to turn this thing into a continuous variable. And it's really easy. And let's just talk a little bit about the notation right now. First of all, P is the population parameter. And this is just the probability of a success. And guys, again, success is relative. N is the number of trials. X is the count out of N that were successes. So what we have to do is we have to take the number of successes, which is discrete, and look at an interval about that by taking x minus a half to x plus a half. So I find out that the probability of winning a particular bet day in, day out is 0.32. I go out in this population and I do 100 trials. I find that of the 100, I had 35 successes. I have to create this interval around 35 by taking minus 0.5 plus 0.5. And my focus becomes on this interval and not the count of x equal 35. Now you're probably sitting there saying, Darbro, you've lost your mind. This is too hard. Well, I'll tell you what, let's work a problem together and see just how hard it is. Okay? I think you're going to find out it's not that hard if you can follow instructions and follow directions, which most of you are doing an awesome job of doing that. So I have this. What is the probability that more than $150 out of 230 eighth graders at a local middle school have been exposed to drugs. Previous studies indicate that 63% of 8th graders have been exposed to drugs. All right, gang. Let's get our notation. What's P? What is the number in this problem that describes the population? Well, this right here. Previous studies indicate that 63% of 8th graders, we're focusing on all 8th graders here. This is just 230 from a local middle school, and 150 out of those 230 say that they have been exposed to drugs. P stands for the statement about the entire population. And again, the entire population here is 8th graders, so we're saying that 63%. Guys, remember, don't ever use a percentage in mathematics. Always convert to a decimal or a fraction. Decimals are easier to work with, so always convert to a decimal. Decimals are easier to work with than fractions. The next thing we want is N. Well, what total number of trials? Well, they chose people one by one all the way up to 230. And then X, in this case, the success. Now here again, success is a relative term. I've seen studies before that are binomial, want to look at the probability that a patient checking into the emergency room doesn't make it, dies, passes away. The success in that particular context is dying in the emergency room. Well, guys, clearly that's not a success in the natural definition of success. But we're not looking at it. We're looking in terms of probability. So again, this problem, the success, is having been exposed to drugs. So we have 150 that were exposed to drugs out of the 230. First thing we have to do here is get the continuity factor. And we call that the continuity correction. And the continuity correction, boys and girls, focuses on the X. It focuses on the smaller number of the total that were sampled. We subtract 0.5. We add 0.5. I had a student one time, I'm going to use a different calculator here in this one. I had a student one time that says, I can't do that in my head. I told her, I said, I don't care. Grab that calculator. So you've got 150 minus 0.5, 149.5. You got 150 plus 0.5. I'd much rather for you to do that than to think that you can do the mental arithmetic and just make, a silly mistake. Okay? So now comes the fun part. We are now in the normal distribution that has mean n times p. So guys, n in this case was 230. And p in this case is 0.63. So the mean is going to be 230 times 0.63. So the mean is 144.9. All right, so I'm going to go split screen here on you so we can see both things going on here. All right. Now we need to get the standard deviation. So the standard deviation is going to be the square root of n times p times 1 minus p. So the standard deviation is going to be n, which is 230, times p, which is the 0.63, times 1 minus p. I'm going to clean this up a little bit. 230 times 0.63 times 0.37. Now guys, we're going to want to run this out quite a few places. So I'm going to go square root of 230. Dogs are going crazy. I rarely get the video that the dogs don't go insane. All right, so I want to go out quite a few places here. So I'm going to go 7.3221. So I'm going to go out, always go out 4 places on a measurement like this. Now, what I've got here is I've got this normal distribution, mean of 144.9, and I am focusing on this continuity correction. Focusing on that interval. So I'm coming out here at x equal 150, which, again, guys, going back to the problem, that's the count. And I want to look at this interval from 149.5 to 150.5. This interval right here is important to me in these types of problems. Now, when I go back to the problem, I go back, what is the probability that more than 150 out of 238th graders? So what I've got to do is I've got to start at this 150, implement that continuity correction, and make my calculations based on the upper bound of the interval built around 150 to correct the fact that we have a discrete measurement, but we're using a distribution that is made for quantitative variables. We call it a ratio scale. Okay, so I have to run my probability from 150.5 all the way up to infinity. Guys, remember on our calculator, infinity up here, we're going to use E99. Now, if this problem came in here and said, what is the probability that less than 150 out of 230? Then I would have to focus on the lower bound of that interval and go from negative infinity, which we should know by now is negative E99, up to 149.5. Okay? So guys, on our calculator over here, we're going to go to distribution, normal CDF. Since we want upper, we're going to run this thing from 150.5 up to E99. With a mean of, I'm just going to type this in. And a standard deviation of the square root of 230 times 0.63 times 0.37. Close that up, go down here and go paste, and find our answer. So guys, our answer here would be 0.2222. Your online course management system, I'm pretty sure, will require you to enter these out to 4 places. Okay? Now, another way of doing this problem, and this is actually the way I like it. Now, I always hesitate to show multiple ways to do problems because the reason is because either way is going to work. But what students will do, sometimes they'll get clumsy and get careless, and they'll use a little bit of that one and a little bit of this one. Guys, that can run into major problems if you do that. But if you're consistent with what you do, this works fine. All right. Now, another way of doing this, let's get back to this problem right here, is to use a different distribution. And this distribution is still normal, but it has a mean of p and a standard deviation of the square root of p times 1 minus p over n. But this focuses not on x, but what we call p hat. And p hat is x over n. Now, it's a lot of notation. Your mind's probably getting ready to explode on you. Just chill, okay? It's going to be fine. I'm going to go through this, and we're going to see that instead of looking at all this and flipping out, we're just going to start with each particular number and try to figure out what that represents. Use what we already know about normal distributions to work the problem. So we've got a normal distribution. And what does this tell us? Mu is equal to p. What's this tell us? The standard deviation is the square root of p times 1 minus p, all divided by n. Notice every bit of this is under the square root. Not like some other stuff that we'll run into. This whole expression, entire expression, is affected by the square root. Focus isn't on x, but on p hat. So we need essentially 3 things. We need mu, we need sigma, and we need p hat. Okay, let's go back to our problem. Mu is the percentage that describes the population because it's p. In this problem, that's 0.63. The standard deviation is the square root of 0.63 times 1 minus that, all over n, which is our total sample size. Well, guys, we've sampled 230 8th graders. P hat is the count out of the whole that has the characteristic that we are measuring. We found out that 150 of these kids out of the 230, you can put this in our calculator. So I can call this about 0.65 of our sample. So about 65% of our sample, which is these 230 8th grade kids, have been exposed to drugs. All right. Guys, we still got to implement the correction. So we still got to implement the continuity correction. Which still focuses on the x out of 150. So we have a p hat lower which is 149.5 out of 230. And we have a p hat higher, which adds the 0.5 as we talked about earlier. out of the 230. Now, for the same logic that we have right back here, we look at the interval, but this time we're looking at the count out of the whole. So we're going to use 150 out of 0.5 because we're looking at greater than. So if we're looking at greater than, we use the upper end of the continuity correction interval. If we're looking at less than, we look at the lower bound where we subtracted 0.5 of the continuity correction. So guys, when we do this on our calculator, let's get this larger right here now because this is what we need. We're going to come into distribution, normal CDF. Now our lower bound is going to be what? It's going to be 150.5. Now a lot of students will stop there. Guys, no, don't stop. You've got to take that out of the 230 students that were sampled. Up to the E99. Guys, in this problem, the mean is 0.63. And the standard deviation is 0.63 times 0.37 divided by the total of 230. And close it up. Don't close it up too soon, because you want every bit of the p times 1 minus p divided by n underneath the square root. Paste it, hit enter, and you'll see that we get 0.222, the same as before. Now, what you've got to do now is you've got to decide which one of these forms do you like best. You might be sitting there saying, well, I don't like either one of them. I get it. I totally understand it. But you've got to determine which of the two forms that, I wish I could see your all's expressions. You're probably sitting there thinking, don't like either one of them. But guys, you either got to, you've got to work with one of these two, okay? And I don't care which one you work out because because as I just showed you, they both come out to give you the same answer. If you want to focus on x, then you need the mean to be n times p and the standard deviation to be the square root of p times 1 minus p times n. And we usually see the n out front here, but we're multiplying. If you want to focus on p hat, which is x over n, then your mean is going to be p, and your standard deviation is going to be the square root of p times 1 minus p over n. Now what's the difference? Right now I think this one is probably easier, just simply because it's easier to focus on x than it is to focus on this fraction. However, this has long-term advantage, because when we get into inference and start looking at confidence intervals and hypothesis testing, our focus will be on what we call our sample proportion. So which one of these you're going to learn, it's totally up to you. You might be in a situation right now where you're just like, Darbo, dude, man, I am trying to survive. I need easier right now. I'll worry about that when the time gets here. Or you might be saying, yeah, I get this. I can work either one of these. So, gang, let's do it. I want to work one more problem. And I want to work this one completely through, okay? Because I skipped a step on the previous, all right, so this one is going to be a complete example. So let's write down the problem first. And let me... Let's do this. So what is the probability that more than 100 of 300 elections will contain voter fraud. Now, based on that, we can't even answer the question. That's like saying I came up with this new game and I rolled a die, 5 times, and what's the probability I get 4? Unless you know the die that you're rolling, and if it's a standard one, obviously has 6 sides, so the probability is 1/6. But what if I came up with this big fancy schmancy die that has like 12 sides to it? So you got to know information about the population that you're actually drawing from. So we'll come in and we'll say one report suggests there is a 32% chance of an individual election containing voter fraud. Okay, now in working this, guys, you got to make a decision. I got a question mark down there. Let me get this. I don't know if that's out of the way or not. You got to make a decision now, left or right. You start mixing and matching these things, you have absolutely zero prayer of ever getting a problem right. If you want to wake up tomorrow and you just decide I want to get every statistics problem wrong that I work, then start mixing and matching these. You got no prayer. You've either got to say, okay, I'm ignoring that right there. I'm living over here on this problem, or I'm ignoring that right here. I'm living over here. You got to make a decision. So I'm going to make the decision right now that I'm going to live here. So my focus is on X, which is, let me get this paper set up here where it looks better. My focus is on X, which is the count out of the whole. That we want to calculate the probability of that of the number of 300 elections that will contain voter fraud. My mean, N times P. Because N is the total elections. P is the report suggesting there is a 0.32 chance of an individual election containing fraud. Standard deviation. It's the square root of N times P times 1 minus P. This is the square root. What's N? 300. What's P? Well, that's our 0.32. And 1 minus P is 0.68. Now, I've had students before, they're like, well, I can't do that 1 minus P in my head. Like, I look at that 0.32, and I can't see that 1 minus 0.32 is 0.68. I don't care. I really don't. We've all got our strengths, and we've all got our weaknesses. If that's a weakness of yours, you're going to be just fine. I know a lot of people who can't do mental arithmetic that are very successful. But to pass this class, get it behind you. If you can't see that mental arithmetic, that 1 minus 0.32 is 0.68, pick up your calculator and punch it in your calculator. I'm okay with that. I'm not trying to turn every single person into somebody get a PhD in mathematics. Sometimes we find things in our undergraduate studies where we just have to survive. And in other things, you find your strengths. So I'm speaking to a broad audience here, so I don't know which one that you fall in, but I'll guarantee you my audience doesn't fall the same place. All right, so next thing we got to do is what? You might be thinking, well, the last time you worked continuity correction. But guys, this time I'm going to actually work a complete example. So we have to check our condition first. And we have two conditions. N times P must be greater than or equal to 5. And N times 1 minus P must be greater than or equal to 5. So the first one I want to work is N times P. So N is 300. My P is 0.32. And when I put that in my calculator, I'll tell you what, guys, hold on just a second. I want to get my other calculator. All right, so checking our assumptions, I have 300 times 0.32. 96, bigger than 5. So check that one off. My next one is I need 300 times 1 minus P. Again, if you need to use your calculator, that's fine. But I see that that's 0.68. And that's going to be 204. That's greater than 5, so life is good. I don't know about life is good, but our conditions are tested. Now, what we need to do now is we need to do our continuity. Correction. X minus a half, X plus a half. Guys, X is my count, so we're looking at 100 out of 300, so minus 0.5. 100 plus 0.5. I'm looking at this. My problem in this situation right here is more than. So my focus is on more than. It's on the biggest part of the interval. It's on the right part of the interval. So guys, what I want to focus on to make my calculation here is I want to go second normal CDF. So I'm 100.5 up to E99. My mean. My standard deviation. So I have N times 0.32, 0.68. And I get 0.2888. Now, for those of you with the other kind of calculator, let me get out of this and show you what happens there. So we're going to go second function distribution, normal CDF. I look at the upper bound up to E99. The mean is 300 times 0.32. And my standard deviation is the square root of 300 times 0.32 times 0.68. Paste, enter again, 0.2888 is the answer. Now, let's say that this one just isn't doing it for you. All right, you prefer the other way. So the other way focuses on what we call P hat, which is X over N, which is 100 out of 300. But for these types of problems, mu is simply P, and sigma is harder to find. I mean, it's got a fraction in it, so that's something that students don't necessarily like. P is 0.32, Sigma is the square root of 0.32 times 0.68 over 300. But guys, we got to concentrate on our continuity correction. So we have to add 0.5 to this. Since we're doing greater than, we look at the upper bound of 100.5 out of 300. Now I'm going to do a less than problem here in just a second and show you how we work on that. Okay, so gang, what we would do here is we go to normal CDF. Now our focus now is what? On p hat. So we have to go 100.5 divided by 300 up to E99. Our mean is just 0.32. And our standard deviation is the square root of 0.32 times 0.68 divided by our sample size, which is 300. And close it up. Come down, hit paste, hit enter, and you'll see we get exactly the same answer. Now guys, I'll tell you what I see all the time, and I just about bet my last dollar that's going to happen here, is students will start mixing these things. They'll come over here and they'll do, well, let me get where you can see what I'm doing. They'll come over here and they'll decide that they want to use the easy mean, this standard deviation, but they'll only put x there. Well, guys, if you do that, your calculator is going to give you a big old fat 0. It's not going to work. You can't interchange these things. That is a wall, okay? This stuff doesn't apply over here and that stuff doesn't apply over here. It's two different ways of working problems. And it's two ways that actually work. All right, let's work a less than problem. So, steps. What are the steps that we need to follow in working these types of problems? All right, choose a method and stick with it throughout the problem. Which method do I prefer? Guys, I don't care. I really don't. Again, I know what's coming, and I know, it's the inference and hypothesis testing is coming, and I know without question that this is the way we're going to do those types of problems. But this over here I think is easier right now. Okay, so just choose a method and stick with it. Check your conditions. Are n times p and n times 1 minus p greater than or equal to 5? Third thing, again, depending on what you're doing, calculate x, mu, and sigma, or calculate p hat, mu, and sigma. The fourth thing, implement the continuity correction to x. P hat's a function of x, so it'll affect that value. X is clearly a function of x because it is x. Calculate that new value. Remember, x minus 0.5, x plus 0.5. The fifth thing, look at the nature of your problem. If your problem has less than, focus on that part. If it has more than, focus on that part. All right, gang, let's work a problem. Let's work a less than problem. All right, let me find one here someplace. All right. What is the probability that less than 140 out of 200 drivers surveyed speed on a regular basis? I'll only say one thing. I'll plead the fifth on this one. Now, what are we missing? Something about the population. State Highway Patrol. Claims or estimates. That 78% of drivers speed on a regular basis. Okay. All right. Now, if I were you guys, what I would do here is I would pause the video and I would see if I could work this problem based on your notes that you've taken. So I would hit pause. I would try this, see if I can get the right answer, and then come back and see me once you work the problem. In the meantime, I'm going to go ahead and work the problem. Okay? Choose a method, stick with it. Well, gang, I'm going to use the method that focuses on x, mu, and sigma. So I'm going to use the one I think is easier now, but doesn't have the long-term effect. Okay? Second thing, work the conditions. N times P. So N is the big number, 200. P is the percentage we have of the population. So 200 times 0.78 is 156, I'm pretty sure. And 156 is clearly greater than or equal to 5, so good deal. Next thing I want to do is check N times 1 minus P. So we have 200 times 0.22. And we have 44. Still greater than or equal to 5. What's the third thing we got to do? Find the values. Well, I'm living over here. That's irrelevant to me right now. I need x, which is the count out of the whole. I need my mu. And I need my sigma. So our standard deviation would be n times p times 1 minus p. And I'm not even going to work those out because we can take care of that in our calculator. What's our next step? Our next step is our continuity correction. That's subtract 0.5 and add 0.5 to our x. Well, guys, our x in this situation is 140. So subtract 0.5, add 0.5. Now, the next thing we get into right here is less than or more than. Which one are we going to focus on? Well, when we look at our problem here, less than is what we're being asked to focus on in this problem. So gang, I now have tunnel vision on 139.5. So I'm going to go to my calculator. I'm going to use both calculators here to show you, just in case. I don't want any confusion. So guys, less than, always, it will never be different than this. Always will always start with negative E99. Some of you have been putting positive E99 there and been getting wacky numbers. Positive E99 is the symbol for infinity. How can it be the lower bound of anything when it's the biggest, the symbol for the biggest number? It can't be left of anything because it's right of everything. So negative E99 goes there. Our count is 139.5 because we're looking at less than. Our mean is 200 times 0.78. And our standard deviation is the square root of n times p times 1 minus p. Come down, hit paste, and go enter. So 0.0024. Would be the answer. All right. Now, what if you're one of those people who wants to fight me on this and wants to use those wacky tables? Now, let's just say that you're okay with the calculator. You don't care about the tables, so you're okay. Do you need to watch this? Yes, you do, because I want to show you something. Tables require you to be able to calculate the Z-scores. And the types of Z-scores we've looked at so far, if we have an observation from a sample, we can calculate its Z-score by taking the value minus the sample mean divided by the sample standard deviation. If we have a value from a population, then we can calculate the Z-score by taking the value minus the mean over the standard deviation, which are mu and sigma for the population instead of x bar and sx for a sample. All right. What does a Z-score look like here? Well, let's think it through. X is well known in these types of problems. Mu, again, depending on the way you solve your problem, but let's just say we use what I call the easy way. And sigma is so for this problem that we just worked, the speeding problem, what was x equal to? It's 140, right? But we needed less than, so by the time we get down here to this continuity correction, the x we need to focus on is 139.5. What are the mean and standard deviation? Well, we know those. We've done those on the previous page. Mu is n times p. Sigma is the square root of n times p, just as we've got right here. So we can calculate the z-score by taking our x minus the mean. So the mean was what? 200 times 0.78. Over the square root of n, 0.22. All right. Now these are situations where the z-score tables are a lot harder to work. So I'm going to go on top. I have the 139.5 minus my mean. Divided by the square root of n times p. And I get negative 2.82. Now, I got to get my table. Hold on just a second. Now, you know the enthusiasm that I exhibit when I go for this table, right? You know how I love these things. So negative 2.8, I'm going to go up here and find negative 2.8. And then I have 0.2. So I'm going to follow this down. And I get 0.0024. What did I get with the calculator? 0.0024. Same thing. Guys, they all require you to find x. They all require you to find the mean. This one requires you to find the standard, or I'm sorry, the z-score. Another option just to keep you honest here. Remember, z-scores follow a normal distribution. Mean 0, standard deviation 1. So another way I could have done this problem, I know you're thinking, holy crap, he's coming up with another way. Tarbell's losing his mind, is to go below the z-score that corresponds to, with a mean of 0, standard deviation of 1, and lo and behold, I get exactly the same thing, within 4 digits. So guys, a lot of different ways to do a lot of different types of problems. We're going to do more of this. So, but really, I've given you an illustration in this video or 2 videos, depending how they actually fall out, how to work these types of problems. So, guys, that's all I got. Take care.